I lost the connectivity. So now I have joined again. So these network issues keep happening. They keep up coming. So again, I hope it's still visible. If it is not visible, then you can tell me. So let me resume from here. That look at how does the depletion region look like in the case of a complete MOSFET. Okay, we had seen this for the case of a MOSFET structure, and look here that this metal line, this is oxide, and this is the emitter MOS. So this particular area is like this particular region is the structure between source and drain. From here to here, metal oxide semiconductor and metal oxide semiconductor. So this particular area is the area for MOS action, MOS structure. Okay, and we had seen the depletion region formation in this particular MOS region. Okay, now when this MOSFET becomes a part of the complete MOSFET device, the situation is like this. We have a source region here, we have a drain region here. Okay, now this let's say this is the source terminal. Okay, and this is the drain terminal, and this is the gate terminal, right? And the condition for depletion region is that for the case of N MOSFET, we should apply a small positive voltage. Small means it should be less than the threshold value. Okay, it should be less than the threshold value. When it is less than the threshold value, you know that there would be a formation of depletion region. Okay, so the depletion region would be of certain depth, certain width. Okay, this is the depth of the depletion region under the oxide, under the gate terminal, right? And note that this region, this boundary line is the p-n junction. This is p-type material, okay, and this is n-type material, okay, and hence the boundary line between p-type and n-type is the p-n junction. So this is the first p-n junction between source and body, and this boundary between drain and body is the second p-n junction. Okay, and what is the state of these p-n junctions? Okay, look at here the source. Okay, so look at here the source, this p type is connected to ground. Okay, this p type is connected to ground. Okay, and although this source is also connected to ground here, here, but one thing we can notice is that we have applied a positive voltage at the gate terminal. We have applied a positive voltage at the gate terminal, and this has got its effect here in this region. Okay, under this terminal. So this has got its effect here also. Okay, okay, and it will slightly affect the whole region of the source in a way. Okay, so you can see that, you can sense that this p-type material is connected to the ground, and although this source is connected to ground here, but still, since we are applying a positive voltage at the gate terminal, so this will have some effect on the source also. And so we can say that the source terminal, the source region would be at a slightly higher potential as compared to the ground. Okay, and because of this, the p-n junction between the source and the substrate would be reverse biased. Okay, would be reverse biased. And when it is reverse biased, we know that the depletion region exists when the PN junction is reverse biased. Okay, and the effect of this positive gate voltage would decrease as we move away from the gate terminal. So as we move from right towards left, the effect of the positive voltage applied at the gate would reduce. Okay, and hence the depletion width would also reduce as we move from this right to left direction. Okay, and this is what is shown here, that the depletion width here in this case is thick, in this case it is more thick, in this case it is thick, and as we are moving in the left direction, we are moving away from the gate, the width of the depletion region is getting reduced slightly. Okay, and this same thing also happens here, that the depletion region would be thicker at this position, and as we move away from the gate terminal, the thickness of the depletion region would decrease as the effect of gate voltage is decreasing. Effect of gate voltage is decreasing as we are moving from right sorry from left towards right. Okay. Okay, so this is how the depletion region formation in the MOSFET device would appear like this. The thickness increases gradually as we move from this direction to this direction. Okay, and it becomes thickest here in this under directly under the gate terminal, which remains of the same thickness. Okay, the thickness is maintained, and as we move again away from the gate terminal, the thickness starts to decrease. Okay, this is the same thing that I have just described. Okay. And inversion layer, again, let us see how the inversion layer gets formed in the case of a complete MOSFET device. Okay, although we had seen this in the case of a MOS structure, but we know that the MOS structure is particularly the part of the complete device. So hence we have to see this once, that how does it looks in the case of the complete MOSFET device. Okay, and the formation of inversion layer happens. We know that when we apply positive gate voltage at the gate terminal, that is just equals to its threshold voltage. So let's say we have some nominal value, we have some value of threshold voltage. Let's denote this by VT naught. Okay, so VT naught is the threshold voltage for MOS device. If we apply voltage higher than its threshold voltage, then the inversion layer is formed. Although it forms even at VGS equal to VT also. Okay, and we say that the conducting channel between source and drain has established. Okay, but if we keep on increasing the gate voltage beyond VT naught, then still the inversion layer is maintained and it becomes more and more strong. Then the inversion layer is formed just at the surface of the substrate or at the interface between the gate and the substrate. Okay, this is the gate area, this is the semiconductor, and this is the interface between the oxide and the substrate. Okay, and just near the surface, near the interface, this inversion layer is formed. Okay, right. And because remember that the depletion region is still there, the depletion region still exists there, because we are still applying a positive voltage at the gate terminal, right? And one inversion layer will be formed, and we know that the inversion layer consists of the minority charge carriers. Okay, in this case it will consist of the electrons. Okay, free electrons, and electrons are the minority charge carriers in the case of a p-type semiconductor, and this is a p-type substrate. Okay, so this is the situation that will look in the case of a complete MOS device, complete MOSFET device, right? And in terms of the energy band diagram, we know that we are applying a potential. Let's say we are applying in this case a potential of its threshold voltage that is equal to its threshold voltage Vt naught, just equal to threshold voltage. Okay, so when VGS is just equal to threshold voltage, we say that the inversion layer has been established. Okay, so when it is just equal to Vt naught, uh, the Fermi level of the metal will go down by an energy equal to Q into Vt naught. Okay, Q into Vt naught, and it will also push the energy bands of the semiconductor, uh, and when the internal Fermi level goes beyond the Fermi level of the p-type substrate by an amount that is equal to phi f. Okay, because it was above uh, Fermi level by an amount phi f. Okay, and when we apply a positive voltage at the gate terminal, then it goes down, and the situation when it goes down by the same magnitude, that is phi f, then that case, that condition, we call that the inversion layer has happened, the inversion layer has been created, and the inversion situation has occurred. Okay, and hence the difference between the Fermi level, internal Fermi level, and the Fermi level of the p-type substrate becomes equal to this 5 plus phi f, that becomes a value of 2 phi f in magnitude. Okay, so this was the condition that we had used in the derivation of depletion width also. Okay, and mm, sorry, not in the case of depletion width, not in that derivation, but we will use it further in the derivation of the threshold voltage actually. Okay, so this is the thing, the same thing that is that I have just explained. Okay, I'll share the slides with you so you can refer to these points later on also. Okay, next there is a derivation of threshold voltage. Okay, threshold voltage. Remember, uh, the definition of threshold voltage is the minimum voltage that is applied at the gate terminal to form an inversion layer, right? To form an inversion layer at the interface between oxide and semiconductor. Okay. So what is that particular minimum voltage? What is that minimum value that we should apply? That particular value is called the threshold voltage of the MOSFET device. Okay. So let us go through the derivation of this threshold voltage. Uh, the threshold voltage has got four physical parameters, four physical components that that contributes in its formation. The first is the work function difference between the gate and the channel. Between the gate and the channel, uh, the remember remember the MOS structure. Okay, the MOS structure. Beneath the gate terminal, we have metal oxide semiconductor. Okay, and the gate terminal is the gate material is different from the material of channel material. Okay, the channel material is a semiconductor, and the gate material can be a metal or a polysilicon. Okay, now since they are of different materials, and we know that different materials have got different work function. Different materials have got different work function, and we also know that when we combine two different materials, because of their internal differences in the work function, there develops a built-in potential across the that across the layer. Okay, so the first part is the work function difference that exists between the gate and the channel, and second part is the gate voltage component to change the surface potential. Okay, we had just seen that we need to apply the gate voltage component, and what is the minimum voltage that is needed to be applied so that we can change the potential of that particular mass structure. Okay, and the third component is the gate voltage component to offset the depletion region charge. Okay, although depletion region does not contain any moving charge, but still we know that the depletion region consists of the ions, the impurity ions, and impurity ions are having some charge. They are having either a positive or negative charge. Okay, although they cannot move, they will not contribute in the formation of electricity, but still, since they are having some charge, so they will have their own electric field. They will affect the electric field. They will generate electric field. Okay, and their offset electric field generated by the depletion region charge, we need to apply a corresponding voltage at the gate terminal. Okay, and that particular gate terminal voltage is the voltage component that is needed to offset the depletion region charge. Okay, and the last component is the voltage component to offset the fixed charges in the interfaces between the gate oxide and in the silicon oxide. Okay. Now there are two interfaces. If you remember the MOS structure, there is a there is an interface between metal and oxide, and there is one interface between oxide and semiconductor. Okay. Now these interfaces between metal and oxide and semiconductor, these interfaces may have some fixed charges trapped inside them. Okay, and if this is the case, that if there is any fixed charge that is trapped in those interfaces, then for nulling the effect of those fixed charges also, there needs to be applied a voltage at the gate terminal so that we can offset the effect of those fixed charges that are there in those interfaces. Okay, so this is the voltage component that is required to offset the fixed charges that are present in the interfaces between the gate oxide and in the silicon oxide interface. Okay, and the combination of these four components will give us an equation for the threshold voltage. Okay, now for n channel, the first point represents the built-in potential of MOS. We know that thing. The work function difference develops a built-in potential. Okay, so if the structure is made up of metal, it will be uh, phi gc. Let's say this is one symbol, phi gc. That is the difference in the work function of the substrate and the work function of metal. Or if it is made up of polysilicon, the gate is made up of polysilicon. Now here it will be a difference in the work function of the substrate and that particular polysilicon materials. Okay, so this is simple. The difference between the substrate work function and the metal work function or the gate work function. Okay, note that the gate can be made up of metal or it can also be made up of polysilicon. So whatever it is made up of, just put up that value, that particular materials work function value in this equation. Okay, now for 2 to get inversion, external voltage required is minus phi 2f. We had just seen just 2 3 slides back. Look at here. To form an inversion layer, what minimum value of energy is required? That is this phi f plus this phi f, that is 2 phi f. Okay, and it is the same. This is the same second point. The gate voltage component to change the surface potential. The surface potential. Okay. So for 2 to get inversion, external voltage required is minus phi 2f. Okay. So to nullify, we require the opposite of this phi 2 phi f, that is minus 2 phi f. Okay. What was the third point? The third point was the gate voltage component to offset the depletion region charges. Depletion region charge. Okay, so we know that the depletion region contain the ions, the donor or acceptor ions, and these particular ions have got their own charge. Okay, so for 3, depletion region charge density at inversion, we had calculated the charge content of depletion region in the previous class, last class. Okay, so taking out that, bringing out that equation here, we can tell that, we can say that the depletion region charge density at inversion is equal to minus square root of 2 q na dot epsilon si dot and magnitude of minus 2 phi f. Okay, where q is the charge, na is the acceptor concentration, epsilon si is the permittivity of the silicon, and 2 phi f is this same value as this one. Okay, and this is the equation when body is connected to the ground, when we connect the substrate to the ground. Okay, but in many cases this vsb, that is the body may not be equal to 0 voltage, just it may be connected to some particular, some small voltage, so that to bring some effect into the device. Okay, so the situations when vsb is not equal to 0, okay, in that case this particular parameter has to be taken into account, and this term will appear here, that is minus 2 phi f plus vsb, and this will give a more general equation for the depletion region charge density qb. Okay, note that this vsb may or may not be equal to 0, but for most of the cases vsb would be equal to 0, but in many cases, in some cases it may not be equal to 0, so keep that point in mind. Okay, third point is taken. Now the last point was about the fixed charges that are present in the interfaces between the two layers, between the three layers. Okay, so the component that offsets the depletion region charge. Okay, this is still about the same point. This is representing the charge content. Okay, and the component that offsets the depletion region charge is then equal to minus qb by c oxide. Okay, where c oxide is the gate oxide capacitance per unit area. Now we need to calculate the voltage corresponding to this charge content, and we know the relation between the voltage, the charge, and the capacitance. So the voltage is given by minus q by c oxide. Okay, where c oxide is the oxide capacitance per unit area. and we know that C is equal to epsilon naught A by T, epsilon naught A by T. So when it is per unit area, this numerator A term will disappear. Okay, and for 4, to offset the presence of positive charge present at the interfaces, that is Q oxide, again gate voltage necessary to offset this charge at interface is minus Q oxide by C oxide. Okay, let's say that some charges are present at the interfaces. So if there is some positive charge present at the interface, that is Q oxide, okay, then the corresponding gate voltage that would be required to offset the effect of these positive charges would be a voltage corresponding to the negative, just a negative with the same value minus C oxide by C, because we know that Q by C is equal to the voltage. Okay, so this becomes minus Q by C, and this particular voltage value will nullify the effect of the charges because of this Q oxide that are trapped in those interfaces. Okay, so now after stating all these four voltage components separately, we need to combine these four components so that we can obtain the overall equation for the threshold voltage. So combining all these equations will give me an equation that let's say this is Vt naught, the threshold voltage, and the first, what was the, remember what was the first point? 5 GC. Then second was QB naught. QB naught is when VSB equal to 0. QB when VSB is not equal to 0. Okay. QB naught, then then the voltage corresponding to this is this one minus QB naught by C oxide or minus QB by C oxide. Okay. Then second point was minus 2 phi F here. Then third point we had seen, fourth point was this voltage Q oxide by C oxide. Okay, now combine all these points, all these components, we will get an equation for threshold voltage Vt naught, that is the first component 5 GC, the second component minus 2 phi F, this is the third component, and this is the fourth component minus C oxide by C oxide. Okay, and this 0 denotes that we have taken the value of VSB as 0. Okay, because this QB naught is the charge content corresponding to when VSB equals to 0. Okay, so this is the threshold voltage when the body is connected to the ground, when the body is connected to simply a ground. Okay, when it is not given any potential, right? But when the body is not connected to the ground, when a non-load is applied at the substrate terminal, then we can say that this threshold voltage Vt would be equal to 5 GC minus 2 phi F minus QB by C oxide minus C oxide by C oxide. So only QB naught would change into QB. Okay, and this will take into account the effect of voltage applied at the substrate. Okay, and we can do a simple manipulation with this equation. We can write this equation as 5 GC minus 2 phi F. Okay, and we can rearrange these two terms in this fashion. Okay, and we can write this equation finally by this equation in terms of Vt naught, because Vt naught is this. Okay, so doing, adding something, subtract something, same thing, okay, will not affect its value. Okay, and we can write the equation for Vt in terms of Vt naught is Vt naught minus Qb minus Qb naught by C oxide. Okay, QB is the charge content of depletion region. QB naught is also the charge content of depletion region. Now this is the case when the body is connected to some potential, non-zero potential, and this is the case when body is connected to some body is simply connected to the ground, zero potential. Okay. Hmm. And we can calculate the value of this term, this particular term. We can calculate the value. We know these equations already. We know these values. So when you calculate, it will come out to be this of this form. Okay, put up this term into the previous equation, and then you will get the final uh, equation for the threshold voltage. That is Vt. The threshold voltage is equal to Vt naught. The threshold voltage when the body is zero voltage, when body is zero, plus gamma into under root mod minus 2 phi f plus Vsb minus under root mod 2 phi f. Okay, and this parameter gamma is given by this equation, under root 2 q n a epsilon si by C oxide. Okay, so look at this equation. Look at this equation, and we can find out the dependence of the threshold voltage on the parameters. So what about the doping density? The doping density is Na, and Na is appearing here. Okay, so and it will come here eventually. So in a way it is directly proportional to Na. It is directly proportional to Na. Okay, so when Na increases, the threshold voltage increases, and it is also proportional to VSB. If VSB is more, the threshold voltage the device will be more. If VSB is simply zero, then it will become zero. Sorry, it will not become zero, but it will become less. Okay, it will become less, and this Q is constant. This epsilon Si, the permittivity of silicon is constant. C oxide, the oxide capacitance per unit area, and phi f, this term phi f, we have seen this earlier also. Okay, we have seen this earlier also. So we can say that this depends on the parameters that Na directly. It depends on the parameter uh, VSB directly, VSB directly. Okay, and VT naught, VT naught is this one. Okay, and there are dependencies on C oxide also. So it is inversely proportional to C oxide. It is inversely proportional to C oxide, and it is directly proportional to Na and VSB. VSB. Okay. Although although the dependencies are a bit complex because they are appearing under roots, and so look at here this under root 2 phi f, and this is again under root 2 phi f. Okay, and this term is differing from this term just by this amount VSB. So particularly the effect is only because of this VSB. We can say that. Okay, because minus 2 phi f under root, and will get cancelled out by this 2 phi f. Okay, and the only difference between these two terms is because of this VSB. Okay, so let us see. Is what is the time? Time is already no. Okay. So this is the example that is taken from the book Kang. Okay, you can refer to this example. You can refer to this example, example number 3.2 from the book Kang, and try to solve this and this, see if you are able to understand this example or not. Okay, then I will discuss this also in the class.